Hello everybody. This video is going to discuss degree centrality for nodes in a network. Many metrics attempt to summarize an entire network. For example, if we're given a network, we may want to know what's the total number of edges inside of that network. We use this information to compare two different networks in terms of different criteria. A couple of metrics that attempt to summarize entire networks are order, or the total number of nodes, size, the total number of edges, number of connected components, and density. In this video, we're going to shift our focus a little bit. Rather than thinking about comparing these summaries or these summary metrics between two different networks, we're only going to focus in on one network. Suppose we're only interested in one network. What we might want to explore is how do nodes within that single network compare with one another. This leads us to a system of different metrics called centrality metrics. And the first metric of centrality that we're going to study is degree centrality. The idea here, again, is to now start focusing for a fixed network, start focusing on the individuals. For example, we may focus in on this individual. One thing we might note about this particular person or node in our network is that she has two friends. In other words, the node degree for this node is equal to 2. We can do this type of analysis for each node inside of our fixed network. Here's a good way to think about it. If you have the network down on a piece of paper, start drawing a circle around the node that you want to find the degree for. Every time you intersect an edge, you're going to increase your count. In this case, we had to cross two edges in order to draw a little circle around this node. So the degree of that node ends up equaling 2. We computed this degree. It's straightforward to see that our friend in the yellow shirt has a degree of 1. At this point, you might want to pause the video quickly, figure out the degrees for the rest of the people. And here are our answers. So when we talk about degree centrality for a network, what we're really reporting is a host of different measures, each one individually related to a particular node inside of our fixed network. So when we look at degree centralities, we're inevitably going to end up looking at a table of values. This table is going to include a list of all the nodes inside of the network, and associated to each node will have the degree, and we'll call that the degree centrality of each node. The formal definition of degree centrality for a node is simply the number of edges connected to that specified node. However, once we start thinking of our networks as modeling some sort of actors and relationships, for example, in a social network, degree centrality takes on its own meaning. Now, if you're considering a social network where edges represent friendships, the degree centrality of a node simply counts up the number of friends for a specified person. Google uses networks to model how web pages are linked to one another. In particular, you can think of the degree centrality in terms of this network as the number of websites that link to a particular specified web page. The applications move on and on. The main point that I want to make here is that the interpretation of a metric depends on the application of the network. So these degree centralities and some of our other centrality metrics are going to have some very interesting interpretations once we know what our network is trying to model. For certain networks, you'll notice some patterns inside of the degree centralities. For example, consider a complete network. In this case, we have a complete network with 6 nodes. And if we look at the degree of, let's say, node B, we can sort of ignore the other edges that don't involve B and then just draw our little circle and count 5 edges that are incident on B. So the degree of that node B is 5. However, the symmetry of this particular network allows us to make an even stronger statement. We could do the same basic analysis with any node inside of this complete network and get the same degree centrality. So one way we can write this is that the degree centrality of any node V is equal to 5. And V here can represent any node inside of the network. We can consider more general complete networks. Suppose we have a complete network with n nodes, so little n is representing the number of nodes that we have in this case. We can still consider the degree centrality for a fixed node. Now we know, since this is a complete network, A is connected to every other node inside of the graph. So we just need to figure out for the centrality, the degree centrality, how many other nodes are there aside from A inside of this network? Well, if there's n total nodes and A is one of them, the degree of A should be n minus 1. Once again, since this argument applies to every other node in the network, we can make a more general statement saying that if you have a complete network with n nodes, the degree of any node is equal to n minus 1. Let's consider one more example. Remember our telephone tree. In our telephone tree, we had one person start the tree by calling two others, each of them called an additional two people, etc., etc., etc. If we want to report the degree centralities, here's one way that we could do it. Think about grouping the nodes based on their degree centralities. So for example, we have one red node, which we might call the root of our tree. We have a collection of 6 blue nodes, which are in the middle. We might call these the branches of our tree. And then we have 8 green nodes, which are at the end of our tree. Reporting the degree centralities of each one of these types of nodes would be a nice concise way of reporting the degree centrality for the telephone tree. Here's a challenge problem. Remember our bucket brigade network. In this case, if we have a bucket brigade with n nodes, how can we figure out what the degree centrality is going to be? Is there a nice concise way of describing the degree centrality for this particular network? Can you spot a pattern? How would you report the degree centralities for a network like this? You won't always be able to find some nice patterns and nice concise ways of reporting degree centralities. On more general networks such as this one, you're just going to have to look at a very large table where each node is listed and each degree centrality for those nodes are listed as well. Luckily, we have computers and algorithms developed by computer scientists to help us do this accurately and quickly.